Hello and welcome to the SoundStage Audiophile Podcast. In this second season of the show, host Jorden Guth is joined by a new guest each episode who knows something about hi-fi that Jorden doesn't. And who knows, while he's learning about all of this, you might learn something too. So with no further ado, here's Jorden and this week's guest.
Hello and welcome back to the SoundStage Audiophile Podcast. My name is Jorden Guth. I am the host for the second season, and today we are joined by two soundstagers to talk electronic measurements. We have Diego Estan, the electronic measurement specialist at SoundStage, as well as the SoundStage founder, Doug Schneider. So, welcome, gentlemen.
Hey, Jorden.
Hey, Jorden. Glad to be here.
Awesome. So today we're going to talk about measuring electronics. And there's actually quite a distinction here between measuring electronics and measuring speakers or headphones or anything like that. So even right off the bat, there's a whole bunch of questions that I have. But I guess to start things off, when we talk about measuring electronics, what kind of things are we actually looking to measure?
I can start by just saying kind of how we're set up to measure. And it's different than the speaker and headphone measurements. Speaker measurements are done at Canada's National Research Council. We have a lab set up at Diego's place where we do the electronics. And we use an audio precision APX 555, which is the industry standard analyzer. And Diego can fill us in on the other equipment. But when we measure the gear, then we are measuring amplifiers, preamplifiers, and DACs primarily, headphone amplifiers maybe. Those come under amplifiers. And maybe Diego can tell us about the setup a bit, and then we can get into what we measure and why.
Yeah, thanks, Doug. Like Doug mentioned, we have an audio precision analyzer with the latest and greatest. It's the gold standard for measuring electronics. We are set up to measure analog and digital devices. So the types of things that we would measure are things like distortion, things like noise, signal-to-noise ratios, intermodulation distortion. And then on the digital side, there's different things that we measure, things like jitter or jitter immunity. So those are kind of the basics, but there's a bunch of different variations on that. So for example, you can measure distortion just at one frequency, or you can measure distortion as a function of frequency, or you can measure distortion as a function of output. So there's a million different variations, and the measurements are pretty exhaustive. They do take me a while, but I think it may be useful for at least some people.
And what I can add in, the measurements are truly objective in a number of ways, because of what happens. It's kind of like, I'm like Clint Eastwood's character in The Mule. I pull up to Diego's place, back in to the driveway, open the back. Usually he pulls some boxes out. Sometimes we put some boxes in, but they go there and they come under this clinical situation where they're measured objectively and consistently. You can repeat the measurements over and over again for what they do.
Now, Diego, you're not typically the one that's writing the reviews or kind of giving the opinions on them. The measurements are one half of this, and then separated entirely is the kind of more subjective review of a product.
Yeah, that's absolutely right. I would never be the one reviewing the product if I'm the one measuring it. And since I'm the one measuring all of the electronics, I don't do the reviews, and that's fine by me. I'm more of an objective guy, and I'd honestly rather do the write-up for the measurements than do the more subjective writing that's involved with the reviews.
Now, when you do measure these, do you then give the measurements to the authors of the reviews before or after, or do they find out same day the measurements as they have their pieces written?
I think Doug wants to answer this question.
Well, yeah, Diego could, but what happens is, just like I drop off the equipment and pick it up, he emails me the measurements. And then the measurements get formatted online. And I know Dennis Berger, who produces this podcast, he's kind of anxious to see them because he wants to know if they correlated with what he heard. And that's a thing. We never show the writer the measurements before they've listened to something, because we don't want to bias them. And so what happens is they see them when they're formatted, and that's often pretty close to publishing date. It doesn't have to be right at the publishing date, but a lot of times it ends up that way just because they're exhaustive to format. And so at the last minute before everything gets put online, many times the measurements are then put online, and that's when they see them, and then the review doesn't change.
Yeah, that's right. And sometimes I'll get the piece before the reviewer, so I collect and make the measurements beforehand, and they get the piece. And sometimes it's the other way around. But either way, that's right. They don't actually get to see them until they've done their review. It's all written up.
Is there a lot of instances where what you measure and kind of the results that you have objectively are like just totally different than the subjective review, either of SoundStage review or other publication reviews?
I would say no, that doesn't happen very often. I guess the one thing to keep in mind is that with electronics, with adequately designed, competently designed electronics, they're mostly pretty transparent, to be honest. For example, they all essentially have ruler flat frequency responses. I mean, there could be variations there in certain situations, but generally, by and large, ruler flat frequency responses, right? So, unlike speakers that can have very large frequency response differences, so it's a more interesting question when it comes to speakers. I would say, did I find the speaker bright, and then you can compare to the measurement in the anechoic chamber. Whereas to say that an electronic component sounded bright, to me, doesn't make a whole lot of sense because they're all essentially perfectly flat in terms of frequency. And generally, if they're competently designed, it's not like they're going to produce enough distortion that you're able to hear noise. Sometimes, yes, that does happen, where someone might note, yeah, this thing's kind of noisy. I can hear some noise from a few feet away from the speaker, and that would be corroborated by the measurements for sure.
But there was a unique situation just recently with the NAD C3050LE. And what Dennis heard was he had to turn the volume up really, really loud on that unit. And when Diego got it in the lab, he found out that the preamp section, there wasn't a faulty device. It's just NAD in the early samples didn't seem to activate the preamp section for enough gain. And he did a firmware update on it, and suddenly there was 12 dB more gain, which was significant. And so there was a situation where Dennis did, hey, for some reason I got to turn up the volume more than normal on this piece, and there it was in the measurements. Here's exactly why that happened.
Yeah, actually, I discovered the problem, and I contacted NAD, which is actually something that's important to bring up. If I find an issue with a component where I measure something and it's really significantly different than what the manufacturer will claim, not a little different or something's a little off, but something's really off, then I will contact the manufacturer to see what's going on. In this case, I contacted them and they acknowledged, yeah, there's a problem. They provided me with a firmware update and it did fix the gain problem. So the thing came shipped with no gain at all, 0 dB of gain, when there was supposed to be 12 dB of gain. So yeah, it made a big difference, especially with the phono input.
And that's really important what he brings up. And I can't speak for all magazines, but I know some magazines have this policy, even on the listening side, do not contact the manufacturer, which is stupid because the manufacturers aren't going to try to swindle you and stuff like that. They've designed the product. And if there's something acting up weird about a product, whether what you're hearing or what we're measuring, just phone them and ask.
Yeah.
And most of the companies, NAD in particular, outstanding engineers there. And they'll say, they'll look into it and research it and stuff like this. And you want to know that you're reviewing the product the correct way.
Well, and you're almost like the first line of defense if like they actually have something that is going to be an issue for their end customers, a publication reviewing it, testing it and saying, hey, is this supposed to behave this way?
And we don't hide that. And we don't hide that. It's in our write-up, the NAD thing. And it wasn't really a flaw with the product, just something needed to be activated. And we don't not disclose that. I mean, there it is. Yep.
Another example of this was a Bryston DAC/preamp. We got an early sample and we found that it was inverting the phase on the digital side. And Bryston saw the measurements and they essentially fixed the problem. So what we do then when we publish the measurements is we don't change them. We show that there's this phase inversion, but we just put an asterisk and say, Bryston has since acknowledged and fixed this problem and current production runs don't have this problem.
Okay, so just for my brain, when you say inverting the phase, what does that translate to in actual speak? Like, would I notice the difference, or is this?
No, it's basically if the signal is supposed to swing positive, well, then it would swing negative and vice versa. Or if you look at an impulse response, instead of going up, it'll go down and then settle. But as long as both speakers have the same phase inversion, you won't hear it. It's a technical thing, and it shouldn't be there, but you're not going to hear it.
So not like a make it or break it.
This is where we could get into signal to noise ratios. That's another thing that's a hot topic. It's an important measurement, but how much does it matter?
Well, yeah. I mean, you can make the point about pretty much all of the measurements. How much does it matter? What can you hear? How much distortion can you hear?
Tell people what a signal to noise ratio is, because it's not a well understood term.
Yep. Signal to noise ratio is the ratio between a signal. Now, the thing is, you have to know at what level that signal is. So if someone just gives you a signal to noise ratio, it's almost meaningless. So you need to know either at what voltage or at what power level and into what resistance or what speaker resistance. So let's say at 10 watts, so signal to noise ratio at 10 watts. So we have a reference signal that's 10 watts into 8 ohms, and it's the ratio of that signal over the residual noise that's measured when there's no signal coming out of the amplifier, if we're talking about 10 watts. And if it's, say, a preamplifier or a DAC, it would be referenced to a voltage signal. 2 volts is a pretty common reference. So manufacturers will often provide signal-to-noise ratios based on their rated outputs. So It could be a 100-watt amp, it could be a 50-watt amp, a 200-watt amp, 300-watt amp. So if you really want to compare apples to apples, you kind of have to change that ratio for a signal that is, say, 10 watts or 1 watts if you wanted to compare all amps for the same signal amplitude or signal size.
And what's a typical signal to noise ratio we see, just average?
Well, a very good signal to noise ratio would be something like 120 dB. An average signal to noise ratio would be more like 92. So I'm talking about kind of rated output. For a rated output, say a 100, 150 watt, 200 watt, 300 watt amplifier. And something okay would be, 90 to 100. And then 80 dB lower, that's the kind of signal to noise ratio that you would see in a phono preamplifier, because they have very high gain and more noise. The more gain you have, the more susceptible you are to noise. So phono preamplifiers, by their nature, will have lower signal to noise ratio because they have more noise. But then what can you hear? I think people need to remember kind of how much signal to noise ratio you can even get in a given room, right? So there's usually background noise, depends where you live, how quiet your room is, right? How quiet the recording is. There's no way you can get 120 dB of actual signal to noise in a regular room.
And then the question is, would it matter? Because this has been a thing I've been watching online. People will compare all these signal to noise ratios. Now, just know that 120 dB, Diego said it was very good. It's really good, right? Mm-hmm. But a designer on one of the forums was chiming in, a former designer for one of the companies, electronics designers, and he said, frankly, you don't need more than 60 dB in a real audio setting. And then I mentioned that to Dennis, and he said 70 dB. And I see Diego, because we can see each other doing this, kind of shaking his head. What do you think, Diego?
I think 60 dB is not enough. I wouldn't want to hear hiss or noise from my speakers at the seating position with nothing playing. Would it matter when the music starts playing? Maybe not, but I just wouldn't like it. I wouldn't want to be able to hear anything coming out of my speakers sitting, 2 meters away. I ran a test once where I encoded a digital signal at different very low levels to see what I could hear in my system, with the volume set kind of at the typical position that I would use, like rather high, just to see what I could hear. And so I started, a signal at minus 70 dB from full reference, minus 80 dB, minus 90 dB. And I could actually manage just to hear a signal at minus 100 dB. But I'm in a very quiet room in the basement. Like, that was with the HVAC shut off. There's absolutely no noise. And I was able to hear just the 100 dB signal, which means I could, in theory, hear 100 dB of signal to noise in my room in those conditions.
So would you care, though, if your component had a signal to noise ratio of 110 or 122?
No, absolutely not. Either would be fine.
And this brings up kind of another interesting thought. Is the recording perfect, right? Is there a hiss in the recording? So let's say you have a perfect signal to noise ratio. Let's say, 120. You would have to assume that the recording artist that is recording this probably doesn't have the setup that's completely eliminating all of the distortion, all of the noise, all of that stuff. So does it matter? Does it actually matter? If you're going to be introducing noise anyways, is kind of aiming for that altruistic 120 worth it?
When you play an LP, you introduce a lot of noise. Yeah. Some people like it.
Yeah, I think it really depends on the recording. Obviously, older recordings on tape, you can hear the hiss. But, modern digital recordings could be awfully quiet and have inherently a lot of signal to noise. But then there's the whole, what's the dynamic range in the recording, the loudest sound versus the quietest sound. So typical pop recordings don't have much dynamic range at all. They might have 10 dB, and then classical recordings might have, 30, 40 dB. So that's another thing to keep in mind. You really need 120 dB of signal to noise when the recording itself only has 10, 20, 40 dB of dynamic range.
But we have an interesting story about signal to noise measurement. Whether it mattered or not, I don't know. But it was the RME ADI2FS digital to analog converter, right? The little headphone output, the IEM output. It was interesting. It didn't look like a problem in that we measured an extremely high signal to noise ratio. So in other words, a lot of signal, barely any noise, but the manufacturer came back and said, you got an error there. Can you explain that one, Diego? Because it was really interesting. Whether or not it matters, our goal is to get it right, not get it kind of right, but get it right. And the manufacturer was claiming their signal to noise ratio was better than ours.
With this particular headphone output, which was designed for IEM in-ear monitors, so things that have high sensitivity, the noise was extremely low, but our measurement was something like 3-4 dB worse than what the manufacturer claimed. So in our measurements, I always supply a table. It's the manufacturer versus our measurements. So I always take what the manufacturers claim, and then I repeat exactly what they claim that they got, with the same parameters. Hopefully they provide the parameters, not always. And then I provide our measurements so you can compare directly. What does the manufacturer say? What do we say? And usually it's very close. So in this case, we were 3-4 dB worse in terms of signal to noise. And I guess an engineer from RME contacted, was it you, Doug? They contacted you?
No, I think they contacted you or both of us. They just group emailed us.
Maybe. Yeah. I can't remember now. And so basically he explained that the noise is so low on this that it really challenges the analyzer. So the analyzer is a piece of electronics like anything else, and it has its own noise floor. So this particular component has a noise floor that's similar to the noise floor of the analyzer. So of course the two get summed together when you're taking the measurement. Now, it doesn't matter for most components, because most components, the noise floor is way above the analyzer's noise floor. Okay, but in this case, it's similar.
And that really speaks well for this product, because you've got a state-of-the-art analyzer, and its own noise out of this product is lower than the analyzer.
It's actually turned out to be right around the same level. But yeah, so it made a difference. It made a difference when you added the noise together. So his way around it was to put a second component in the chain when he measured his device. So another low noise device, then you add the second device, then you subtract away the noise that you got when you added the next device. That was his solution.
So you establish a baseline with the additional device, and then you add on top of it. It's like when I need to measure my kid, I basically take my kid onto the scale, do that measurement for the weight, and then put the kid down and measure myself. And then the difference is how much the kid weighs.
Yeah, exactly. So, but I figured that I could do this by characterizing the self noise of the analyzer, which I did. And then when I was subtracting away the noise, I still wasn't getting the right answer, and I was scratching my head a little bit. So I actually emailed the Audio Precision, the makers of the analyzer, and they're quite helpful. They always answer right away. And they said, well, when you add or subtract noise, you have to do it in quadrature. I'm going to nerd out a little bit here, but when you have two uncorrelated signals, you can't just add them together, because they're just moving around. They're completely random, right?
Yeah.
So you can't just add them. You have to add them in quadrature, which is the square root of the sum of the squares. Okay, that's how you would add the two noise components together. And as soon as I read that, of course, I know that. I mean, you learn this in high school physics class when you have two.
I didn't learn this in high school physics. Just going to put that in there.
You might have. It's like when you do an experiment and you have a scientific measurement and you have uncertainty. If you have two sources of uncertainty, they're both uncorrelated. And if you want to add them together, you have to add them in quadrature. You don't just add them together.
The difference is Diego listened in high school.
Yeah, that might be the difference right there.
But it's also, I also do this in my day job. I deal with uncertainties in scientific measurements, and why this didn't dawn on me for noise, I don't know. But when you have uncorrelated noise, you can't just add it together. You have to add it together or subtract it away in a certain way. Okay. So anyway, I did this. I carefully characterized the noise of the analyzer, and then I subtracted it away the right way. And RME's claim was 121 dB of signal to noise, and I measured 121.4 dB of signal to noise. So
no way.
Yep.
That's
got
crazy.
The right answer finally.
There you go. Now, again, bringing this back to the average person, would that make a difference for the average person?
No. The bottom line is this thing is dead quiet. You can plug in the most sensitive in-ear monitors you can imagine. You just won't hear anything out of them, which is nice.
That's really cool.
So even any noise out of them, you'll only hear the sound.
Yeah, any noise. Which certainly isn't true for all headphone outputs. I mean, a lot of headphone outputs, you won't hear anything, but if you go find the most sensitive earphones you can possibly find, you'll probably hear something. But you wouldn't with this. It's just dead quiet.
So that's really interesting. Electronics that measure so quietly that you wouldn't be able to hear it even on the most sensitive headphones or monitors that you can get.
Yeah, and so quietly that they challenge the analyzer.
Yeah, challenge the state-of-the-art electronics.
Yeah, and there are other components that challenge the analyzer in terms of distortion as well, which we can talk about.
Yeah, well, let's take a break, and that could be what we start up with after the break. And we're back from that short little break. Diego, we left off talking about other measurements. One that I'm curious about is distortion. So can you tell me a little bit about distortion and generally what it is and how you can actually measure that?
Sure. I might have to nerd out a little bit again. So distortion, if you can imagine a pure oscillating sine wave, okay? We know that music is made up...
Just up and down.
Up and down, okay?
Yeah.
And music is made up of a bunch of these sine waves at different frequencies, and there's harmonics, which I will touch on in a second. So if you can imagine this pure, pristine, oscillating sine wave of 1 kilohertz is kind of the standard that you show most measurements around, although other frequencies as well. So a perfect sine wave that has no changes to the shape would have no distortion. And the way the analyzer checks for distortion is that it does what's called a fast Fourier transform on the waveform. So that's just basically applying some fancy math to change a time-based signal, which is the alternating sine wave over time, to change that into a frequency-based graph that you get to see. So the frequency-based graph will show you the signal peak. So if we're talking about 1 kilohertz, you'll have a nice peak at 1 kilohertz. And then if it's not perfect, you'll have harmonics. So you'll have the second harmonic would be at 2 kilohertz, the third harmonic will be at 3 kilohertz, the fourth harmonic at 4 kilohertz, etc. Right? The lower those harmonics are, the purer the sine wave and the less distortion there is. So really distortion is just a sum of those harmonics, how big they are and the sum of them. That's what distortion is.
And how is distortion introduced into electronics? Like, is it just the quality? Is it the type? Is it having like the power too close to the input kind of thing?
That's a good question. So having the power too close to the input, that would be a way to get noise. So we can talk about noise. So I guess I can touch on noise. No, there's two types of noises. There's uncorrelated noise, like I talked about, like just from thermal noise. Like even just a resistor in a circuit will have some noise that's just random.
Is it true that electronics have inherent noise, right? At extremely low level?
Yeah, they do. So, and then you can have correlated noise, which is basically picking up electromagnetic interference from these transformers that are in the power supplies that are sitting inside the electronics. So, in North America, we run at 60 hertz, right? That's our power supply. And so you will almost always see, not always, some designers are very good at suppressing this, and some types of power supplies suppress them very, very well. But usually you will see at least a small peak or a bigger peak at 60 hertz, and then the harmonics of that 60 hertz, 120 hertz, 180 hertz, and you can see it all the way up. So that's the noise part, okay? Right, the harmonics of the 60 hertz.
Yeah.
The distortion part is the harmonics of the signal itself. And pretty much any electronic component is going to create some degree of distortion. The analyzer itself has a signal generator, right? It has a signal generator to make the signals to feed the thing that I'm testing. The signal generator is not perfect because it's made up of electronics. So it has some distortion, albeit extremely low distortion, but you can see it in these FFT graphs. You can see the little peak at 2 kilohertz when your signal is 1 kilohertz, and another little peak at 3 kilohertz. But they're tiny, but they're there. There's some distortion from the analyzer itself. That is to say, when I'm feeding the output of the analyzer to the input of the analyzer. So the signal generator to the analyzer. No piece of electronics in between. I'm just looking at the raw performance of the analyzer. There's still some distortion, very, very low, and there's some noise, very, very low.
And what's called crossover distortion, not the crossover of a speaker, but crossover distortion in an amplifier is a thing, right?
Yeah, that's when you've got transistors that are turning off and on for the positive and the negative leg of the signal.
Okay.
And when the signal crosses the 0 point, there's when the transistors are basically one's turning off and the other one's turning on. That's what's called crossover distortion, and it's corrected with feedback. But the point is that electronics are going to cause distortion one way or the other.
All electronics inherently have some amount of noise and some amount of distortion.
Yep, absolutely they do.
And the goal is to have as little as possible to get the closest representation of the music as possible.
I would say that's my goal, but I would imagine that some audiophiles would argue that it's not important, and what's important is what it sounds like, because people do claim that devices with high distortion sound good. Like, for example, tubes have high distortion, but they have a certain type of distortion that could be pleasing to the ear. I personally would rather have something that is very low distortion. I just want it clean.
So that actually kind of brings me to this other thought, which is there are things that we can measure that we may not be able to necessarily hear, right? We can measure it. We can see that it's amazing. We might not necessarily be able to hear it. Is there things that we can hear that we might not be able to measure?
Let me jump in here first, because I want Diego to them, but I hear this a lot, and I have an issue with things, because you'll get, particularly on I don't want to blanket because I'm a subjective audiophile, on the subjectivist crowd, they'll say, well, I heard this, and it didn't show up in the measurements. And my first question is, did you actually hear it? Because many people can go down a rabbit hole. They'll say, oh, I switched this and I heard a difference. Now, if you play two things identically, first time and second time, you'll hear a difference even if they're identical. So before we decide that I can hear it and not measure it, we should decide first, can you hear it? Okay, that's a real thing. And that is often not examined, that you actually heard a difference. And a good example is when I sent two identical CDs out to a bunch of writers, 2/3 of them thought they heard a difference between them. They were identical, bit for bit identical, exactly the same. And they thought they heard a difference. That's not to say there might not be a difference. And I would say the big thing is maybe we don't hear certain things that we measure. They don't matter as much, or maybe we don't measure everything, because Diego can speak to this. I think his measurements are the most exhaustive in the industry. I haven't seen anything as extensive as what he produces for us, but he could do 10 times more.
Yeah. My 2 cents, I'm an objectivist, but I'm not an absolutist. So I won't say it's impossible that there's something that we can hear that we're, not that we can't necessarily measure, but that we're not measuring, or that we're not aware how to measure. It's possible, but I think it's highly unlikely, is my position. And to Doug's point, yeah, most people, when they say, I heard this, I heard that, I doubt that they actually did. And I would be the type of person to say, prove it. And the way you prove it is you have to first level match to 0.1 dB, the two, and then you have to perform an ABX test, and you got to score 8 out of 10 or better. And if you've done that, then you've proven to me that the difference is real. So
very scientific.
Yeah. And the old adage of trust your ears is just horrible advice. It is really bad advice. You should not trust your ears unless your eyes are closed and you don't know what you're listening to.
And Diego just scared the hell out of so many audiophiles by saying that. But there is truth, because the whole blind testing thing and this and that scares the hell out of audiophiles. But what's really interesting about it, particularly with speakers, once you do blind tests, you realize there can be big differences. You can hear the differences, but only when there are differences.
Yeah, I should have obviously put a caveat there. We're talking about competently designed electronics. Speakers, you can listen sighted, you can trust your ears. There's big differences. You can measure it after and easily corroborate, what you heard to the measurement. But competently designed electronics is another thing altogether.
I've got an interesting thing. I was in Las Vegas in a cab with some distributor, and I had to just tell him. He said the stupidest thing imaginable. I said, "Hey, did you see these electronics?" And he said, "Yeah." I said, "What did you think? Did you listen to them?" And he said, "No." "Did you see how bright they are? They'll sound just like that."
How bright they are, like physically, like the
physically
design.
They were bright. And I said, "That's one of the stupidest things anybody's ever said to me." But you know what? They do tests and they show, and you have a brightly colored thing and you go, "Oh, that's bright." Something dark sounds warm and chocolatey. You can inject bias into listening tests really, really easily.
Yeah, you absolutely can. Yeah, but I take your point, and I don't discount the feeling that you get from buying something. I've done it myself. I buy based on measurements, of course. Now, again, I'm not talking about speakers. I got to listen to the speakers, but I buy based on measurements. But I also buy based on things like build quality, what it looks like, what it feels like, the reputation.
Diego I've seen his system, and unlike those objectivists who have some shitty little $250 ramp and these crappy little speakers, Diego has a pair of Focal Sopra #1s. He has Macintosh gear. He has top flight gear because he likes the engineering. He likes the build. You can respect the build. You look at a Macintosh component, you look at a Bryston component. Hey, maybe I can't hear these differences, but I can sure admire the way they're built, where they're built, the warranty behind them, all that.
Yep. And that's all perfectly legitimate.
Yeah, I can imagine that as well. Like, especially with amps, right? Like, some of them are quite large. So if you're going to put this large thing in a living space or in any space that you're going to spend any amount of time in, you want it to at least look a certain way and kind of give you that nice feeling. You don't want to be looking at kind of an ugly box or something like that.
Completely agree.
And with amplifiers, there can be huge differences in the sense of, if an amplifier is not powering a speaker well, if it's not providing the current necessary and stuff, you can hear those differences. Those are readily audible.
Yeah, I'll agree with that. With amplifiers, you can. So assuming that the amplifier is competently designed and it's operating well within its performance envelope, and it can drive the speakers that you want to listen to at the levels that you want, and it's still well within its linear range, far from clipping, that's when I would say that there's no audible difference. But if you're driving it hard, past the performance envelope, your speakers are a very difficult load, and the amplifier has a hard time with small loads, then yes, you can hear those differences.
So, and this kind of, there's two trains of thought here. One is I'm thinking about the speakers and what makes a speaker hard to drive. And the other kind of thought process that I have is the opposite true? Can there be electronics that are too powerful for the set of speakers that you have? And can that have a negative impact as well?
So a speaker that's difficult to drive would be one whose impedance or let's just call it resistance, drops very low at certain frequencies. So, when you see specs for a speaker, you'll see 8 ohm nominal or 4 ohm nominal. Yep. That's pretty typical, 8 being probably more typical, but it's not 8 at all frequencies. They all have varying resistance or impedance with frequency. So at one frequency, it could be 8 ohms, but at another frequency, it could be 5 ohms. At another frequency, it could be 16 ohms, right? And this is something that we measure when we measure speakers at the NRC. We'll plot the impedance curve versus frequency.
Okay.
So a speaker that's difficult to drive would be one that drops down into the 2 ohms. Sometimes some of them drop even below 2 ohms. And it's even worse if that dip happens in the bass region, because that's where there's more musical energy and in recordings, and you require more power. So the lower the resistance, the more current is required from the amplifier, right, to maintain that signal. right?
Yeah.
And that's what makes it difficult for an amplifier. And for an amplifier to be able to do this, it needs to have a big and robust power supply to deliver the current, and typically a lot of output transistor devices to be able to handle all that current and all the heat dissipation. And your other question was, can you have too much power? I mean, the short answer is no, but of course, yes, if you turn the volume up too high.
If you go to the extreme, right?
Yeah, if you don't treat your ears very well, you'll also mistreat the speakers, and you could potentially. But it's certainly more dangerous to have an underpowered amplifier driving a speaker, because you could potentially drive it into clipping, and when you clip, you chop off the signal, right? That sine wave that you're supposed to have. Well, you cut it off and you make an edge, and making that edge creates a bunch of harmonics, high frequency harmonics, and that goes right to your tweeter, which is not built to handle a lot of power. So it's definitely worse to have low powered amplification than too much power for your speaker.
So if I was an audiophile starting out and I was debating whether I should invest in a higher quality speaker or higher quality amps, knowing that this was going to be like a stepping stone product, it would be fine to like step into a much more powerful amp than I had speakers for currently, as opposed to the other way around.
Yeah, you could go ahead and buy a very powerful amp and not have to worry about it. And then you can buy whatever speakers you like.
And you know what? I got that advice from a store owner. It was really good advice in the 80s. Speakers make the biggest difference. And he said, but you know what you want to do first? Buy the best, most powerful amplifier you can. Because what'll happen is you'll constantly be upgrading your speakers and you'll never upgrade that amp.
Interesting.
Yeah, amplifier technology, well, a certain type of amplifier class technology hasn't changed much, honestly, in the last several decades. There's been some improvements, which we can talk about, the very low distortion Class D amplifier that I wanted to bring up, if you'd like. That would be the Eigentact amplifier module. We got an early sample. Doug got one, and it was not for sale, but it was kind of a prototype, I believe, Doug, right?
Yeah, from Purify Audio. And I'll just give just a brief background. Peter Lingdorf, who I call the Elon Musk of Danish hi-fi, well, European hi-fi, because he seems to own all these audio companies, hired some of the best and brightest engineers, including Lars Risbo and Bruno Putzis and others, to create audio technologies to be used in other companies' products. And one of the things they first came up with was what they called the Eigentact amplifier module. And it's a Class D. It's a type of amplifier class. Diego can explain it, but that's getting into the weeds. But it performs extraordinarily well. And that's what Peter, when I met him in Poland and he was talking about it, and that's why we got one of the engineering samples, he really wanted to get one to us first.
Yeah, I measured it fairly recently, because Doug got it a while ago, but then recently decided, we should probably measure it, and we can publish the measurements, because the amplifier.
And you know what? I haven't published those measurements, and you just reminded me. And it was because we didn't have your lab set up when I got that amp. So we gave it to an engineer in Toronto to measure it, and we published that. But then we wanted it published from our lab with our current battery measurements.
Right. And because it had become popular, it's been used in a few different NAD amplifiers recently that we measured. So I did the full suite of measurements, and boy, this thing is impressive. So in total harmonic distortion, at the 10 watt kind of standard that I use, 0.00004. So 4 zeros. And just to compare, that is scratching the level of the analyzer. The analyzer's signal generator THD number is 0.0002. So 4 zeros and a 2 versus 4 zeros and a 4. Okay, so just close.
Very minor differences.
Yeah, there's a little bit more, but extremely low distortion and noise as well, extremely low noise as well. 125 dB of signal to noise ratio. This is A-weighted at 200 watts. Just remarkable.
What does 8 weighted mean?
A-weighted, the letter A. The A weighting is just a way to kind of mimic the way the human hearing operates. So, your ears are more sensitive in the middle frequencies and less at high and less at low. So basically, it's a type of weighing that you apply to the noise to kind of mimic what you would hear if you were listening to the noise. Okay. And it's just an industry standard. A lot of manufacturers just use A weighting. But anyway, the really, really good signal to noise. This thing is dead quiet, and the distortion is extremely low. And it has been used in a few amplifiers now. And I think it brings up a good question that we can broach is this thing going to commodify high-end amplifiers? Are high-end amplifiers just going to just put one in their amp and make a nice big metal case, sexy case, right? With the meters or whatever they want, but they just put this module inside and they know it's going to be perfectly transparent. It's going to measure great and it's going to sound great. I think it's already starting, but I don't know, Doug, if you have kind of thoughts on that.
Yeah, I want to put into perspective those distortion figures. Dennis Berger on SoundStage Access wrote an interesting article about measurements, and he cited some, I'll put this in the show notes when we publish this, measurements of how much distortion we can hear. And I think it was, I'm going off the top of my head, I'm not looking at it, but I think it was 4% for jazz or something like that, 1 or 2% for another type of music, and 0.1% for pure sine waves. In other words, a pure tone. Anything below 0.1% you won't hear, but 0.1% you might hear. So Diego is saying this thing's got 0.0004. Yeah, 3 zeros and a 4. So
4 zeros. 4 zeros.
4 zeros and a 4. Each time you add one of those zeros, that's like a lot. So this thing is so far below. And again, it's beyond the thresholds. If 0.1%, like in Dennis's article, is with a sine wave, you'll never hear the noise and distortion. But it's kind of cool to have an amplifier. And I've got that engineering sample, and I've got the NAD still with me, the M33 that's based on it. It's really cool to have an amp that's that quiet and in ways that affordable. I think the NAD amp is $3,500 or so, less than $4,000 anyway in the US. And it's basically as good as you can get if you want purely transparent sound. Now, some people do love some distortion, some tube sound. We know that tubes can produce higher distortion. And some people say it makes a more euphonic and pleasing sound. And I've got a amplifier that I'm taking to Diego, a 300B based amp, puts out a whopping 15 watts, okay, that he's going to be getting next week or the week after to measure, but I want him to listen to it first and see, hey, does it sound good?
It will have a different sound for sure. So yeah, well, and back to that Purify Eigentakt amp module. I think, Doug, you mentioned that it's going to be it's getting put into or has been put into a T+A high-end amplifier design.
Yeah. Not again, it's not ultra expensive, and Dennis wrote about that in the article. He put that in there. They have it in a mono block and in a stereo amp, and they put their own spin on it with their own power supply. And I think they have a damping factor adjustment. And inherently, though, it's got low noise, low distortion again. You can see the amp module's performance in their own published specs, and I hope we get one of those amps in to measure as well.
Yeah. So I think this might become more common with high-end manufacturers. I mean, if you've got this thing that's out there that's basically perfectly transparent, why not use it?
Exactly.
Will all the companies use it? Or like, would some companies look at that and say, we could do better or we could do different?
I think the different is the thing. Some will say we can do better, but I presented that question to, I won't say the company because he didn't say it to me on the record. He said it casually, but he's been one of the top electronics designers for decades, and he recently retired. He said the problem with the thing like that is it kind of makes the amp into a commodity, and suddenly the manufacturers have trouble differentiating themselves with it. And differentiation on the market is not an insignificant thing. You have to make yourself stand up. Now, with the Purify thing, you can throw your own power supply in there like T+A did. They got the damping factor adjustment. So they've put a spin on it. And I think that's what has to be done. But yes, you run the risk of making it into a commodity.
Yeah.
Whether it's a good thing or a bad thing is up for debate, I suppose. I think it's a good thing as an objectivist. Just have a good standard that's out there and just buy based on looks and build. A
standard. You know what? I've always maintained the two great standards. Well, one great standard has always been the Bryston 4B, rock solid Class AB amplifier. This is actually a great standard for Class D amplifiers.
Let's just, for my brain, Class A, Class AB, and Class D. When we're talking about amplifiers, I understand that one of them is digital. Is that Class D? One of them we don't use at all, which is like Class B. Give me some background on amps here.
Yeah, you got it basically right. Class D is a digitally driven amplifier.
Okay.
Class A and Class AB.
Well, not digitally driven. It's on-off state, right? That's what you mean.
I mean the control of it is digital. It's on-off, on-off. Of course, the output is analog. It has to be. Okay. But a Class A and Class AB amplifier is just a typical linear amplifier. You put in a small signal, you get out a big signal. They use transistors at the output stage, other transistors to drive the voltage up in the first stage. And the Class A versus Class AB is just the amount of biasing. How on are the transistors in the output stage?
Yeah.
So if they're all the way on, it's Class A. People think it sounds better, but it's quite wasteful as far as energy. So that means whether you have a signal there or not, they're just always on.
Yeah.
There's always current flowing through those output transistors. Class AB is kind of a hybrid between Class A and Class B. Class B is that the signal turns on the transistor. So if you got no signal, the transistors are off completely. So it could be used in telecommunications where you need efficiency. Class AB is, always a little on, but not all the way on.
Okay.
Right. And then you might still have a little bit of crossover distortion that you can correct with feedback.
And that's the most common type of traditional amplifier out there.
Class AB.
Class AB.
Class AB, yeah.
Now, again, going back for the beginning audio enthusiast, are you going to be able to tell the difference? Would you kind of say no to buying a specific amp because it's Class D instead of Class AB?
So personally, I would not say no just because it's a Class D amplifier. I mean, technically, the Eigentach would be, I think, classified as a Class D. I think it operates a little differently. The problem I have with a lot of cheaper Class D amplifiers is that they have high output impedance, so a low damping factor, and that depending on the speaker that you use and its impedance, you can actually hear the differences at high frequencies. It might sound slightly brighter or slightly less bright, and it depends on the speaker. So ideally, you want an amplifier that has an extremely low output impedance, which means a high damping factor, so that any differences in impedance in the speaker doesn't really change the frequency response.
It doesn't translate right away.
Yeah.
And there's something that can be seen in the measurements because, well, if you just measure one thing, if you just do it into an 8 ohm load, you won't see that variation. But once you do it into a 4 ohm load, 2 ohm load, you see the variations.
Yeah, and a real speaker, which is something that we do, and I think people appreciate. We measure frequency response not only into an 8 ohm resistive dummy load and a 4 ohm resistive dummy load, but also a real speaker to show the frequency response when a real speaker is hooked up to the amplifier. And then, and how much does distortion matter? I can go to the other extreme and talk about the amplifier that I measured with the highest distortion. This was the Atoll IN200. It had 0.3% total harmonic distortion at 1 kilohertz. So I think Doug mentioned, 0.1, you might be able to hear 0.1 in a pure test tone. Probably not music, though. But the general rule of thumb, though, is that, your amplifiers, you're probably not going to be able to hear the distortion if your amplifier's got 0.1 or less.
Okay.
Right? So this thing measured 0.3, but at 20 kilohertz, as high as 3%.
Oh, wow.
Although it's harder to hear, distortion at 20. I can't hear 20 kilohertz at all anymore. Yeah. I'm too old. But anyway, 0.3% at 1 kilohertz. So this kind of intrigued me. Compared to your typical amplifier, there was, 1,000, 10,000% more distortion, right?
Yeah.
So I decided to take it down and listen and see if I could hear a difference. Again, I'm an objectivist, so most of the time now, after many years of doing this, when I carefully level match two competently designed components, I don't hear a difference with my eyes open when I know which is which. Okay.
Yeah.
So I did that. I carefully level matched with a voltmeter, not an SPL meter. You got to use a voltmeter to get it good level matching. And actually, I thought I could hear a difference between this amp and my Macintosh amp. So, all right, next step is to do a single blind ABX test. So I asked my lovely wife, Kathleen, if she would be so kind as to do the switching for me. So basically, really, you should do a full 10 tests, but I thought we should just do 5 at first, not to drive her crazy, just to see how well I do with 5 tests, right? So she randomly decides which one is she going to play, A or B, right? The Atoll or the Macintosh, 5 different times. I don't know which is which, but I'm supposed to correctly identify after having spent much time listening to both. And I think I know what the difference is, right? Well, it was an epic fail because I got 1 out of 5 right, which is worse than just chance.
Yeah.
Right. So there you go. As soon as it was completely blind, even though this thing has relatively high distortion for a solid state amplifier, like pretty high, the Macintosh is quite low. I couldn't tell. So
interesting.
Yeah.
I mean, it goes back to the idea where there's other elements to this, to the products that you decide to purchase, than just measurements. However, the measurements are kind of setting a bar, setting the standard to say, well, people took the care to at least get this kind of, I'm going to call it a noise floor, but that's not the correct term.
Noise and distortion. I mean, both those are the two big things.
Not just took the care. I look at the measurements where what I glean most from the measurements is competence. Diego mentioned power supply noise. If you see a modern amplifier that has a ton of power supply noise, like an obscene amount, then you know that maybe this isn't a competently designed amplifier. If you see obscene distortion and the circuit doesn't justify it, like if you got a no feedback amplifier, you're going to have higher distortion. But if it's got obscene distortion or some anomaly or something, it's not just poor measuring, it might be incompetent. And that's also what I look for in speaker measurements. Does the person or team who designed it know what they're doing? And I don't know if we've ever come across anything incompetent yet, have we, Diego? I don't think so. No.
And I don't want to claim that Atoll amp is incompetently designed. Some manufacturers have different philosophies.
Amp. It's actually a low feedback amplifier.
And that's the reason.
It hit its power rating. We don't have to get into what feedback means, but as soon as you got super low feedback, you got higher distortion because feedback's used to correct distortion, right, Diego?
That's right. So I don't want to say it's incompetently designed, not at all. And different manufacturers might have different design philosophies. That's all. And in their case, maybe they don't care. Well, I can probably say they don't care so much about distortion. It's on the high side, but maybe they just say, well, we listen and it is what it sounds like that matters to us. That's fine. It was still hitting. Let's just say there weren't any claims that were unjustified. They weren't making any claims, and then I took a measurement and said, "Oh no, that's not what they actually claimed." Everything was above board. It made the power ratings.
And I'll tell you this: Jay Lee did a video about that amp. Dan Kong reviewed that amp, and there are many people around the world who are Atoll fans. But I want to throw in one other. Actually, we didn't talk about this measurement that I think we're the only ones that do it. That Diego does, and it affects integrated amplifiers and preamplifiers. And this is a huge thing that you can hear. Channel balance. Is the left channel identical to the right channel when you turn the volume control? And you know what? You'll hear that. If it's off a dB or two to one side, you're going to hear that with a skewing to one side. And Diego does a measurement on the integrated amplifiers because they have volume controls and preamplifiers. And that's one of the most important things, I think, that people should look at.
Yeah, this was something when Doug and I were first discussing, what are we going to do for these measurements? What are we going to include? I'm pretty sure Doug had this at the top of his list. It wasn't on my radar, to be honest, because I've never seen it in any other publication. Not to say that it's not out there, but I just hadn't seen it. And basically, I produce a table. Anytime there's a volume control with a device, I produce a table, and I show the channel deviation. So the difference between the left and the right channel in dB at different volume positions from minimum to maximum and a bunch of steps along the way.
Oh.
Okay. And this is quite important to Doug. And I agree. If it's enough, like 1 or 2 dB, you could hear a skewing of the center image.
Yeah. And if you go to some, older components that use potentiometers versus these modern control methods, and I mean, it's a big thing to me because I had components when I was younger and in the past at very low volume levels, one channel would start playing before the other one would.
That's common,
right? And then they get more accurate in the middle. And there used to be this thing in the 80s and 90s was use your volume between the 9 and 3 o'clock position because that's where it's most accurate, right, Diego? With those old potentiometers. And so to me, channel balance, in fact, I look at the channel balance just on the outputs when he does the left and right channel for everything. It should be the same on both sides.
Yeah, of course. Anytime you have a volume control, it's not going to be perfect. Although I'll mention one device that was essentially perfect. But you have different ways to implement volume. You have a potentiometer, which is basically like a wiper scraping along a resistive element. Okay. So you got cheap potentiometers because you have to vary resistance basically.
And those were used all the time in the 60s, 70s, 80s, 90s, and even up till today.
Even up to today. So you have cheap potentiometers that can have, up to a couple dB of channel imbalance, especially at the lower part of the volume. Then you've got very good quality potentiometers that you can still find in high-end gear that you got to pay a lot of money for that have better tracking, better balance between the channels. But most commonly today would be integrated circuits that have transistors and resistor ladders inside the integrated circuit, and you basically switch the transistors on and off to switch the resistors in and out of the circuit, and that's how you control the volume. So it's digitally controlled. You're turning these switches on or off, but it's still in the analog domain. So the signal is passing through different resistors and different transistor switches. That's most common. You can get pretty good channel balance that way. Then you can build a discrete version of that, which would be with relays and resistors. So high-end gear tend to have that. But then you have this one manufacturer that uses this one volume control technology that I was just floored by. This is AccuPhase out of Japan.
Okay.
And I measured the C2850 preamp. And they have a different way of doing it. Now, I don't know exactly how it works, but just basically reading their literature, that what they say is they convert the voltage signal into a current in 16 different levels, and they can turn these levels off and on. So that gives you up to 65,536 steps, 16 bits. They only use 251 steps. It would be kind of insane to use all of those steps. So they implement 251 steps in their volume. So the one great thing about it was, in the low part of the range, it was 5 dB increments. So because you want bigger changes in the low part of the volume.
Yeah.
And as you increase, right, it would get smaller. And when you get near the top of the range, it would be 0.1 dB changes. Very, very small. You can't even hear 0.1 dB. But very, very small changes at the very top end. Just exactly what you would want.
To fine-tune everything.
Yes. But the amazing part was the channel balance or imbalance. It was perfect. It was the worst I measured was 0.0006 dB, and that was at the low part of the range. Okay. And most of the way through, it was 0.000. I couldn't measure an imbalance with the audio precision. And to give you an idea of how good that is, if you were to build a traditional volume control with resistors, to get that, you would need something like 0.01% tolerance on your resistors.
Yikes.
Which I don't even know if you can buy. Like, good resistors are 1%, and very good tolerance resistors are 0.1%, but you'd need something in the 0.01% tolerance range to get this. It was essentially a perfect volume control.
So, and maybe this is a dumb question, but when you're talking about channel imbalance, could your speakers themselves, because left and right speaker obviously might have slight differences in their construction and stuff. Could the speakers also be an issue?
Yeah.
And then do they correct that?
Okay. No, and I can speak to this, okay, because I measured speakers for over 20 years. Really good manufacturers try to get them within a 1 dB window. This is why I also tell people, hey, two speakers that look like they measure the same should sound the same. And I'm like, no way, because manufacturers have trouble making two identical speakers sound the same because you get variations. Really good manufacturers try to get within a 1 dB window across the frequency range. 1 dB possibly. Poorer speakers, and we've measured, could be 3 dB difference. And there are people who is like, oh, the image is shifted to the left. Now imagine you have a 1 dB shift on the left on your crappy volume control, and you have a 3 dB shift to the left at a certain frequency on your speaker. Suddenly you got 4 dB to the left. Okay. Yeah. That's realistic. It could happen. Okay. It could happen. So you want everything as close as possible. And electronics are relatively easy. Maybe Diego can speak to why. Speakers are really hard to get exactly right.
Then there's the room too, right? I mean, if your room is not symmetrical, then you can have more room gain on one side of the room than the other, and then that could affect how much output you're getting from one speaker. Well, it's not the speaker itself.
Do any of these amps or electronics actually have the ability to change?
Yes, it's called the balance control.
The balance control.
And in more modern, so the old balance control is to compensate for that sort of stuff.
Okay, that makes sense.
And room correction, which will look at the output of the speakers and try to vary that and make it even. Yeah,
that would be the modern way of doing it. Yeah, but the old way was just the balance control, and we've all seen it, right? It was kind of crude. You wouldn't be able to get 0.1 dB increments. You'd probably just move it a little, and you're probably at a dB or so. But yeah, that was the traditional way, and now you can do room correction.
So with everything that we've talked about so far, whether it be the channel balance, which is definitely the eye opener for me this episode, I didn't even consider that being a thing, to distortion, to noise, you need really good equipment and really good analyzers to do that. Diego, tell me a little bit more about some of the equipment and kind of what makes it so good.
Sure. So yeah, the resolution capabilities of the analyzer when you're looking at different frequencies. Remember earlier I talked about the FFT, the fast Fourier transform, and it's what you do to kind of plot over the frequency range where the signals are lying and where the harmonics are lying. So the resolution of the analyzer is really good. So an example I have here is a preamp that I measured one time, the SPL Director Mark II, had a very low distortion, but some noise, not high noise, but some noise. And when I looked at the FFT for 1 kilohertz, so you got that signal peak at 1 kilohertz, and then you have the harmonics of the signal, 2 kilohertz, 3 kilohertz, 4 kilohertz, et cetera, et cetera. So when you just kind of glance at the FFT, it looks like there's a 3 kilohertz peak, which would be the third harmonic, right? It would be distortion. It would be the third harmonic of the 1 kilohertz signal. So that would be considered total harmonic distortion when you just glance at it. But actually, when you zoom in, you can actually see that the peak at exactly 3 kilohertz is a lot lower, and that the peak I was seeing zoomed out was at 3.06 kilohertz, which is the 51st power supply related noise harmonic.
Oh, wow.
Yeah. So if you take 60 hertz 51 times, it's the 51st harmonic of the 60 hertz. So it's actually noise. So this thing has the resolution to differentiate between the distortion peak at the 3 kilohertz, which was much, much, much lower and buried in a bunch of other noise related harmonics.
Yeah.
And so you need something with a lot of resolution to be able to do that. But this analyzer has the resolution to show peaks all the way up past 20 kilohertz from that 60 kilohertz initial peak.
Interesting.
And it's not a concern. The peaks are low in level.
Yeah.
But this analyzer allows you to see them.
It's like a super powered microscope. You're seeing the finer grain and the finer details.
And that's not uncommon. The engineer who measured the eigentakt at the beginning said when he moved to the APX 555, he was seeing power supply stuff he never saw before. And so the designers are a bit at the mercy of the resolution of the equipment.
Yeah.
Interesting. Now, there is also people that really don't like measurements. Like, don't show me things that show that it's different. Like, this is what it is. That's my belief.
Yeah. Here's the thing. If I was to err on one side, I don't like what's happening on certain forums where it's all about the measurements. They just look at the measurements and they decide what something sounds like based on the measurements. They haven't even listened to the product. And then you get the extreme where somebody says, I don't want to look at the measurements. I just want to listen to it. Well, if I had to pick one of those two, I'd pick the listening to it, because ultimately you have to take the thing home and listen to it. You have
to enjoy it. Yeah,
you're not buying it to please a piece of test gear. You do have to listen to it. And I think it was Steve Guttenberg said once in one of his things, and this is where I agreed with him. I said to Brent Butterworth, I'm going to agree with Steve on something. Why don't you just listen to it? Well, why don't you just listen to it? Now, of course, you don't have to take the extremes. You come somewhere in the middle. And this is what I tell people. The measurements are what they are. You don't have to look at them, or you can look at them. You know, when we traveled to England and the Netherlands, we came back and got the wickedest cold, all three of us, right, Jordan?
Yeah. Jesus.
And mine lingered I never go to the doctor, ever. And I went to the doctor because it lingered for 2 weeks, and she said, you got a cold. And I'm like, okay, that's what it was. But she said, you're the kind of guy who never comes to the doctor, and I'll never see you again if you don't get sick. So I'm going to get you to do a bunch of blood tests. And I'm like, why? And she said, just to see where you're at. And I'm like, I feel fine. She said, you'll never come back, just to see where you're at. And I'm a little nervous to go get my blood test because I don't really want to see where I'm at. Because what if something comes up that I don't know? This is the exact same thing with measurements. What upsets many of what I'll call the anti-measurement people is they might see something in the measurements they don't really like. And suddenly that might rattle them.
Ignorance is bliss.
Ignorance is bliss. Likewise, the guys who are all about the measurements, and they'll look at a speaker measurement in particular and say, well, that can't sound good. And then you listen to it and it sounds great. Uh-oh, we've got, a really cognitive dissonance here. I don't like what I see. I just say to people who are really anti-measurement, hey, I actually side more with listening, because ultimately you got to use it. But they are what they are. Just accept it. And you know what? The way we do measurements of speakers at NRC and the way Diego measures electronics in the lab, it's repeatable. It's not like it changes one day to the next. They're very repeatable. They are what they are. Live with it. Now, you don't want to live with it if you've got a wicked channel imbalance. You want to get rid of that gear. You want to sell it as quickly as possible, because that means you got a piece of shit. But other than that, hey, if it's got a little higher distortion or this or that, it is what it is.
Awesome. And to close off this episode, I'm going to ask a question that I ask to everyone that comes on this. Diego, if you had to put on a couple different songs or a record, let's say, what would be the soundtrack to your life that you use when you're enjoying music?
I'm gonna go Canadian, okay, because I'm Canadian. So I'm gonna put Colin James up there, Blue Rodeo, Tragically Hip. I'm gonna put those three up there.
Awesome, Doug. I don't think I've actually asked you this before. What's the soundtrack to your life? What's the jams?
The one album that jumps out at me is because I read the book called Making Rumors. I've revisited Fleetwood Mac's Rumors, and everybody should listen to that album at least 30 times to memorize it. It is a phenomenal album. It is really an epic album, and the book Making Rumors is fantastic, but the making of that album. But if I were to pick something modern, Lana Del Rey is like the best new thing. When you listen to her recordings, the Norman effin' Rockwell one onwards, they're just phenomenal. She really makes great albums. So that's my number one today.
I need to add some more tunes to my playlist. All right. Thank you both, gentlemen. Until next time, take care, everyone. All the best.
Thank you.
Thank you.